following program is brought to you by Caltech.
Our next speaker is Natalie Batalha. She's a professor. She received her bachelor's degree in physics from UC Berkeley, her PhD in astrophysics from UC Santa Cruz. She is the deputy science team leader for the Kepler mission. And she now is going to share with us how Kepler goes about finding exoplanets.
All right. Thank you so much for having me, and thank you so much for braving the drizzle and joining us here. We really appreciate it. I'd like to talk to you about something that's very near and dear to my heart, something I've been working very hard on for the last 11 years of my career, which is the Kepler mission, NASA's 10th Discovery mission. I think both Eric and Jason have mentioned the Kepler mission already, but I'm kind of curious to know how many of you had never heard of Kepler before setting foot in this audience. So if you're brave enough to clap if you had never previously heard of Kepler, could you do so? Excellent, good. All right, otherwise I was going to go home, but I'll stick around. Okay, what is the objective of Kepler? As I said, it's NASA's 10th Discovery mission. It is a space telescope, except that it's not, unlike the Hubble, it's not orbiting the Earth. It's actually orbiting the Sun. And its objective is to determine the frequency of Earth-sized planets in or near the habitable zone of Sun-like stars. Or more simply put, it's to figure out if planets like Earth are common or rare in our galaxy. And I think we all probably feel, well, of course they are. Why should we be special? But simply imagining or using our intuition and actually knowing are two very different things. And Kepler wants to actually accumulate scientific evidence so that we know for certainty what the answer to that question is. All right, habitability. In order to understand that and design a mission, you have to think about what the ingredients for life are. And, well, in our context of our biology, that's really easy, right? I mean, pepperoni pizza and red wine are like right up there. But if we step back and we look at every nook and cranny here on Earth, we find that the question of life is actually a little more complicated. Under every rock we seem to lift and look under. Every remote corner of our planet, there seems to be some kind of life lurking. We have life such as these cyanobacteria, the blue-green algae, which comprise the very oldest fossils that we know about. They're more than 3 billion years old. They did not require oxygen for existence. We go to the very coldest places on Earth, like in Antarctica, and we dig down kilometers underneath an ice cap, and we find a lake there that we see via radar. And in the ice core just above this lake, we find dormant organisms that suggest those organisms might be living in the lake underneath. And on the opposite end of the spectrum, we go to some of the very hottest places, like in the middle of this thermal pool in Yellowstone National Park, where the temperatures exceed the boiling point of water and acidity levels are very high, and we find life. So as diverse as these organisms are, the one thing that they all have in common, no matter where on the tree of life they reside, is that they are carbon-based. And that's probably not a coincidence. Carbon has very special properties. And we know that organic chemistry, or carbon-based chemistry, requires as the solvent for facilitating chemical reactions, water. Water is that solvent. So it seems to be that water is the common thread. And so we base our definition of habitability on the existence of water. And when we look for habitable planets, we look for places where liquid water might pool on the surface of that planet, as Jason's already described. And so here we've got this notion of the habitable zone. It's this green zone around each of these stars. We've got stars of different properties. Some are small and cool, some are larger and hot. And where the habitable zone is going to depend on those stellar properties. Now, if we find an exoplanet and we can measure its orbital period, we can use Kepler's laws of planetary motion, which are some 400 years old, and figure out how far from the parent star that planet is. And therefore deduce if it's habitable or not, assuming that we know something about the stellar properties, and hence the name Kepler for our mission. Okay, how is Kepler going to find planets? Well, what we propose to do is measure the brightnesses of stars very, very, very precisely, and wait for cases where the orbital plane of the system is inclined so that when that planet is orbiting, it passes right between our telescope and the disk of its parent star, thereby blocking out some of the light from that star. And so here we measure the brightness of the star itself as a function of time, and we see these little telltale dips that happen when that blocking or that eclipse event occurs. And if it's truly a planet, it'll happen not just once, it'll happen several times, and from that we'll be able to get the orbital period. Now this event here is going to last some 4 to 12 hours, something like that, potentially repeat only once per year. So we have to have patience. We have to look at these stars very, very carefully without blinking, measure their brightnesses very precisely, and wait for these little dips. Now here's a cartoon of a star like our Sun and a planet like Jupiter. Jupiter will take away about 1% of the brightness of the parent star. So you put 100 light bulbs together, you take away 1, and that's the brightness change you want to measure. Seems simple enough, but a planet like Earth is this tiny little dot right there. And a planet like Earth is going to remove 1 part per 10,000 of the brightness. Put 10,000 light bulbs together and take away 1. And that's what we're attempting to measure. In order to do so, in order to measure brightnesses so accurately, you need a big enough light bucket to collect enough photons so that you can make a precise enough precision, precise enough brightness measurement. And here's the blank for the mirror that is in the Kepler telescope. So it's about what? About a meter, meter and a half across. The effective aperture ends up to be about a meter. Whereas a telescope like Hubble is more like a little bit over 2 meters. So that gives you an idea. And you need a camera. You need to put a camera on the back end of it. And it's kind of similar like the cameras that you guys have, your digital cameras. You know, that have the little CCD inside of it that measures the light, except that the CCD in your camera is about the size of my thumbnail. And the CCD in the CCDs, plural, in their camera is about 1 square foot of silicon. And here it is being lowered into the hardware, onto the spacecraft bus in the photometer. Here's a picture of the spacecraft itself before launch. It's about the size of a minivan, and it weighs about as much as a VW Bug. And here it is being lowered into a vacuum chamber where we could control very precisely the thermal environment, how much it shakes, so that we could simulate the conditions it would encounter in space and understand exactly how our spacecraft would behave. All right. Now, stars are not all oriented so that all planets will transit, right? Stars are oriented in random directions. So in that sense, this is kind of a numbers game. We need to observe lots of stars with the hope that we will see some that are edge on. And there's a probability you can calculate for that happening. So we want to point our spacecraft where we know there are a lot of stars. And we know where there are a lot of stars, right? Right in the plane of the Milky Way galaxy. And this region is actually a region you might be pretty familiar with, except, of course, in the city you're not used to observing so many stars, right? However, here in this diagram, we've got 1, 2, 3 very bright stars that you might be familiar with. They comprise the summer triangle, Vega, Deneb, and Altair. And if you look up in the sky in the beginning of the evening during the summertime, you'll see them right overhead, the three brightest stars overhead. And so this is more or less where Kepler is going to be observing. Let me now put in the cartoons. Here's Lyra, Vega, Deneb, the tail of the swan. Here's our swan's wings, and then Altair over here. And the Kepler field, represented here with this little cartoon, every square being 2 CCDs sandwiched together as an array comprising 42 separate CCDs, nestled under the wing of that swan Cygnus between the bright stars of Deneb and Vega. So up in the sky, this area that we're staring at, this patch of sky, is about the size of your fist if you hold it at arm's length. That's 100 square degrees. By astronomical standards, that's pretty big. Even a full moon is only about a half of a pinky finger. So there are lots of stars in that field. Nevertheless, we're actually probing a tiny region of our galaxy, the closest stars being some tens of light years away and the furthest being some 3,000 light years away. So a relatively small region of our Milky Way galaxy. The spacecraft was launched March 6th of 2009, and just to give you an idea, this technique for finding exoplanets was proposed in a publication dated 1971. Our principal investigator himself published a paper on this in 1984. So from idea to fruition, you're talking about something like 30 years of one's life. This proposal to do this was rejected 4 times. Right? Persistence is the key. A month later after launch, we took our first light image. So this is an actual image from our telescope. You see this same pattern, this same mosaic from our CCDs. And here's some cutouts. We've got a globular cluster over here. This is a cutout from this little postage stamp with a very special star whose name is Trace 2. This is an object we knew already had a transiting planet orbiting it before we even launched. So we were paying special attention to that guy. So now let me take one of these modules, one of these CCDs, rectangular, and chop it in half and show you a blow-up of what that looks like. And that's what you see here. And this gives you a feel for the density of stars. In this one field of view, there are 4.5 million stars to choose from. And we select, over the whole entire field of view, 150,000 of the best. The brightest, light-wise, bright, and the most sun-like. We want sun-like bright. And so we pick them from these. You can see some other interesting features if you stare long and hard. You see some are fuzzy, like this, and these. Those are actually galaxies outside the Milky Way that we're imaging here. Okay, well, let's look at some actual data. Let's go back to Trace 2, and let me show you what its light curve looks like. And by light curve, I mean brightness measurements as a function of time. And every point on here is a measurement of brightness as taken by a modest ground-based telescope that discovered this object. And so this jitter that you see, this up and down, is not real. It's not intrinsic to the star. That's noise. It's kind of like trying to measure the distance between San Francisco and New York with a 12-inch ruler. And this is what it looks like with GPS. All right, so that's Kepler data, where the error bars, the noise, they're actually smaller than the size of the symbol that we've used to plot this data. In January of 2010, at a meeting of the American Astronomical Society, we announced our first 5 planet discoveries, and here's their family portrait right here. We've got cartoons illustrating the stars and their relative sizes correctly drawn, and the sizes of each of the planets that orbit them, and how they cross the disk of their star from our vantage point. And down below them, we've got the light curves. And you can see when the planet-to-star ratio is larger, then you block out more light, right? This is a relatively large planet, so you've got a deep transit. Whereas this little guy, about the size of a Neptune, has a very shallow transit. These 5 discoveries were detected by Kepler via transit photometry and then confirmed by ground-based radial velocity measurements. That Doppler, that wobble that Jason was talking about. And this is a very powerful thing to do because transit photometry tells you how big the planet is in size, in radius. The wobble method tells you how massive it is. And if you know the mass and you know the radius or the volume of the planet, you can get the density, mass divided by volume. And if you know the density, you know if it's rocky, if it's gaseous, if it's a water world, an ice giant. And in this case, we know these are all gas giants. Yet they're very different than planets in our solar system because they orbit so close to their parent star. These 5 discoveries were done using only the first 43 days of data from the Kepler spacecraft, which means that their orbital periods are very short in order for us to detect many transit events. In fact, they orbit about 10 times closer to their parent star than Mercury does to our sun, Mercury being the planet closest to our sun. And so that means their surface temperatures are in excess of 2,000 degrees Fahrenheit, so don't buy real estate. Okay, a little bit of a retrospective on transiting planets. The very first one was detected, actually it was discovered by the wobble method, but then also found to be transiting via photometry. And this is HD 209458. I've got radius of the planet plotted on the y-axis and the orbital period on the x-axis. And this guy is short period, bigger than Jupiter. And that was in the year 2000. Ground-based transit surveys to find planets were really only beginning. And so it took a while in order to make a decent number of discoveries. I'm fast-forwarded now 5 years, and I have a handful. And again, they're all short period and around Jupiter-sized. And let's fast-forward another 5 years, June 14, 2010. Many more discoveries, but again, they all seem to cluster at short periods and Jupiter sizes. And that's simply because those are the easiest ones to find, especially from the ground, although we are starting to push down to smaller planets. Okay, on June 15th, 2010, Kepler released a catalog of objects that look very interesting in that they have transit signatures indicative of a possible planet. But these are systems that are not yet confirmed via radial velocities. They are simply candidates, and we'll call those objects of interest. But I'm going to include them on this plot so you can see where they lie, if indeed they do turn out to be bona fide planets. And remember, I'm plotting radius versus period. 306 stars were released on June 15th, all of them with transit-like signatures. So even if half of these turn out to be false positives, things that are not planets at all, but some other astrophysical signal mimicking a planet transit, this is still a significant discovery. And what's very interesting about this result is that the majority of the Kepler objects in this catalog are Neptune-sized and smaller, and at longer periods, even though we're still using only the first 43 days of data. As Eric pointed out, in late August of this year, Kepler announced another system, Kepler 9, B and C. 2 planets, both transiting and orbiting the same star. Confirmed in that we now know their masses and their sizes and hence their densities, and they are both very similar to Saturn-sized objects, both in size and density. There was a serendipitous discovery, though, that was made about this in this same system. As we started looking at it more closely, we found a very, very shallow transit event at a much shorter period, I think something like 1.6 days. And if this is confirmed, this will end up to be the smallest planet that Kepler has found so far at just 1.5 times the radius of the Earth. So here is a figure that you've seen already. It puts the Kepler planets that have been confirmed so far into the context of the other planets with regards to mass and density. Again, you get density if you can confirm the planet. But really, Kepler is beginning to play kind of a different game because ground-based telescope time to confirm these planets using some of the world's largest telescopes is a very expensive endeavor, very time-consuming endeavor. And yet here we have, hundreds of candidates. And so the game we're starting to play is more of a statistical game. We're going to be telling the public these individually might have a 90% likelihood of being a bona fide planet. But yet, if we find 100 of them, and we say to you 90 of them are probably real, that's going to be meaningful, right? So we're kind of moving, at least for the short term, until the ground-based telescopes can catch up, both in time and in technology, so that we can confirm the smaller mass planets. We're going to be playing this kind of a statistical game, and so you'll hear about that in future announcements. This is a plot that's kind of like the one I showed you before. We've got radius here, but on the x-axis I changed from period to surface temperature. Remember, with the period, you can get the distance from the star, and then you can estimate what the temperature is on its surface. And I put this to show, this really compelling region is down here. This would be the habitable zone, or at least the region where you've got liquid water between 273 and 373 centigrade. And then this green zone marks kind of a 1 Earth radius to 2 Earth radius, spanning Earth-sized planets up to super-Earths. So as we collect more data, we will be pushing out to longer periods, right, because we've got a longer time base. And also we will be observing more and more transits, which means we increase our precision so that we can push down to smaller planets. So you will see over the next couple of years Kepler making announcements that are pushing to this bottom corner. And that's going to be very exciting. Again, Kepler's objective is to answer the question if Earth-like planets in our galaxy are common. But of course, the bigger question that we all want answered is whether or not we're alone. It's a question that humanity's been asking since humans communicated, really. It's evidenced by popular culture, right? I mean, the popularity of movies like Avatar, right? We want to know. And sure, it's great to dream about it and to imagine it, but it's going to be a completely different experience when you look up in the sky and you point to a system to your child and you say, you see that star? That has a planet that we know harbors life. That's a completely different thing. And finally, the creatures of the water here on Earth left the ocean at some point in time, right? Some of them did, and changed evolution. And in that same sense, human beings will one day leave planet Earth, and it will have that kind of a profound impact on our evolution and where we go. And maybe we will have to do it for survival. But maybe also we have to do it because inside of us is that seed, that seed that makes us always search for a new horizon. That kind of drive that pushes us towards the unknown. I don't know. But I believe that one day from the shores of a new world, we'll gaze at the sea that took us there, and in this time, its waves will be stars. Thank you.
This program is brought to you by Caltech. Visit us at caltech.edu.